I will just introduce myself briefly. So my name's Fran. I'm a tutor with Oxbridge Applications. So a bit of background to myself. So I studied physical natural sciences at Cambridge, and I specialised in materials science, and I'm now doing my master's in science policy. So that's a bit about me. So welcome to the Premier Service talk on nanotechnology and nanomaterials. So today we'll be looking at the past, present, and future of nanomaterials. Hopefully it will be quite an interactive talk. It would be great to have some engagement from you guys. I'll be asking you questions, and of course you can ask me questions anytime. I'll do my best to answer any questions you might have. So as an overview of the session, we will be looking at an introduction to nanotechnology, working with some definitions, then looking at the history and the development of nanotechnology. We'll be looking at nanomaterials as well, some examples, their applications as well, and then the future scope of nanotechnology and the potential applications and potential problems that nanotechnology and nanomaterials can solve in the future. So a question for you all before we get started is, at the moment, what do you know about nanotechnology and nanomaterials? So I know this is something that is covered at GCSE and A-level to some extent. So do any of you have any kind of prior knowledge about nanomaterials or nanotechnology?
I think it's just very small materials that can be used to make up something that's stronger with even though they have a lesser weight.
Fantastic. Yeah, brilliant, Alex. So something very small, absolutely. So scale is definitely part of it. And you also mentioned properties. So nanomaterials have very interesting properties, and that's why they are so special and widely researched. Fantastic. So, introduction to nanotechnology. So what actually is nanotechnology and why is it important? So in the chat on here, I will be adding a file, and in the PDF, hopefully you guys can see it. Hopefully it's just uploaded. So this is a nanotechnology quiz, which if you open it up, hopefully you'll be able to fill it in, or at least note down some of your answers along the way, just to make sure it's a bit more interactive. I won't be testing you at the end or anything like that. It's just for your own learning if you're interested. The recording link, I think it will be available on YouTube possibly. You can get in touch with the Oxbridge Applications contact after the session for that. Okay, so nanotechnology, it's often dubbed the science of the very small and explores the world of materials and devices at the nanometer scale. So this is a realm where individual atoms and molecules hold sway over extraordinary properties and phenomena. So it's really, really interesting stuff. More specifically, nanotechnology is the imaging, modeling, measuring, design, characterization, production, and application of all these structures, devices, and systems at the nanometer scale. So what we mean is atomic, molecular, and macromolecular scale. We call these special materials nanomaterials. So as their name suggests, these are materials structured at the nanometer scale, where individual atoms and molecules dictate their properties. So what do we mean by small and nanoscales? So dimensions between approximately 1 and 100 nanometers are known as the nanoscale. So in terms of this, to help you visualize the kind of nanoscale, here's a few images that can perhaps help you understand just how tiny it is. It's often hard to grasp how tiny the nanoscale is. So here we've got, obviously we know that a nanometer is 10 to the minus 9, or a billionth of a meter. The human red blood cell is about 7,000 nanometers wide. Fingernails grow at about 1 nanometer per second. And a really interesting one, I think, is that if we take a tennis ball and compare that to the size of the Earth, that is the same scaling as if we consider a tennis ball and a nanometer. So quite an incredible scaling there. Another important criteria for the definition of nanomaterials and nanoscales is that nanomaterials have to be man-made. So it has to be a synthetically produced nanoparticle. Otherwise, you'll have to include every naturally formed biomolecule and material particle, which in effect means you'd have to redefine the whole of chemistry and molecular biology as nanotechnology, which I don't think the biologists would be very happy about. So nanomaterials are synthetic. So let's go on a brief sort of journey through time, looking at the past uses of nanotechnology. Many examples of civilizations through time where they have sort of inadvertently engaged in nanotechnology centuries before we even had the name nanotechnology and nanomaterials. We'll look at some examples from ancient Rome, from the Mayan civilizations to medieval Europe. And we'll see how nanotechnology has always left a mark on our collective history throughout the world. So first of all, starting with ancient times to the 20th century. The 20th century is really where everything kicked off, but there were many uses of nanotechnologies prior to this. I don't know if any of you have heard of the Lycurgus cup, but this is an ancient use of nanotechnology which dates back to the Roman Empire. So this amazing piece actually dates back to the 4th century AD. And artisans in the Roman Empire created this special cup. As you can see, the cup changes color depending on the angle of light. So it's a really, really amazing piece. It's currently in the British Museum, of course, but it's a really amazing sort of feat of nanotechnological applications. Might any of you suggest sort of how this works, maybe what it could be made out of to allow it to show these amazing sort of optical properties?
Is it something to do with polarizing light?
Yeah, really interesting suggestion. So essentially we have tiny particles of gold and silver in the cup, and these are only tens of nanometers in size. And since they're embedded in the glass, when you have very, very small particles of gold and silver, the angle of light essentially affects its optical properties. So hence it sort of changes color depending on where the light is coming from. So moving forward then to the Middle Ages, we are all familiar with the amazing works in European stained glass in cathedrals and churches and so on. So stained glass windows are actually another example of the use of nanoscale particles. In this case, the vibrant colors come from nanoscale metal particles within a glass matrix. So the interaction between light and the nanoparticles creates these amazing colors. As you can see on the image in the right, we have gold particles and silver particles in glass. It's a similar concept to the Roman cup. And depending on the size and the shape of the nanoparticles, this affects the color that we observe. So we're able to achieve some really interesting combinations of colors using gold and silver nanoparticles. It's interesting as well that not only the size of the particles, but the shape as well affects the color that we observe. Moving forward then to across continents to ancient India. So we're going back in time now, and we encounter some pretty cool uses of nanomaterials. So researchers in India quite recently have found evidence for the earliest known carbon nanotubes, and these date back 2,500 years. So these nanotubes have been found in these ancient pots, like the ones you can see in the image on the left. And these come from archaeological sites in Tamil. Essentially, they used these vegetable fluids or extracts to coat the pots, which could have led to the formation of the carbon nanotubes during processing. So in the past, they regularly added this sort of plant sap or vegetable fluid extract to pots before placing them in the kilns. And it's thought that when they did this, this resulted in the pots being a bit more durable and tough. And so they would have continued to add the plant sap and maybe repeating the process. So they likely knew that the technique to make the coatings was beneficial and useful to the properties of the plots. It's unlikely, obviously, that they knew this sort of thesis with any kinds of formula, or that they were actually applying nanotechnology. So it's a really interesting use of nanotechnology, which is kind of inadvertent. Another example is the famous Damascus steel, which is known for its exceptional strength and flexibility. So this steel has been used in swords throughout the Middle Ages in India. And this type of steel is produced through a forging process that results in nanoscale carbide and carbon structures inside the steel. So this means this kind of steel is highly sought after, especially in the ancient world. And finally, let's not forget about the Maya blue pigment. So this is another really great example of nanotechnology applications in the ancient world. So the Maya civilization in Mesoamerica dates back to the 3rd century and up until the 10th century AD. So the Maya blue is a very durable pigment, and it's created by embedding nanoscale clay particles within a matrix of organic materials. The pigment was often used to decorate pottery, as you can see, and murals and statues. And it's kept its beauty and its pigment throughout the ages because it's exceptionally stable. Until recently, this feature has really confounded scientists, and they weren't sure why it's such an exceptionally stable pigment. Many pigments from the ancient world degrade over time. And so when we look at murals and pottery from the past, often we're not left with any colors and pigments. But Maya blue is a bit of an exception. So it resists attack by solvents, by acids, bases, and also withstands temperatures as high as 3,000 degrees C. And so because it's so stable, it's made the chemical analysis of Maya blue very difficult, as it cannot be created with common reagents. It was only in the 1960s that scientists were able to show that the pigment was composed of 2 main ingredients. So they used spectroscopic techniques to identify indigo, which is a vegetable dye, and then another ingredient, which is an unusual sort of magnesium aluminium clay. And then even more recently, a tunneling microscopy analysis of the pottery that you can see on the right, that's called the Field Museum pottery. This showed that in addition to the indigo and the minerals, they found copal, which is a natural resin. And this being present is possibly why the Maya blue pigment is so resilient. So some really interesting applications of nanotechnologies in the ancient world. And of course, they wouldn't have exactly known about nanotechnologies and what they were actually doing, but we can see that it's really made its mark on the ancient world. So now let's move on to the early 20th century. So fast forward, we witnessed some really key pivotal moments that essentially laid the groundwork for modern nanotechnology. So first moment I'd like to talk about is Richard Feynman and his work. I'm sure you've all heard of him and come across his lectures. Many argue that the actual official history of nanotechnology starts with Feynman's classic talk in December 1959. So that year, the renowned physicist delivered his famous lecture titled "There's Plenty of Room at the Bottom." And in this lecture, he envisioned the possibility of manipulating matter at the atomic and molecular levels. It was a very revolutionary and visionary talk and inspired generations of scientists and essentially set the stage for nanotechnology revolutions. The second key moment was in 1974, so a couple of decades later. So the Japanese engineer Taniguchi coined the term nanotechnology. He used it to describe the precise manipulation of materials at the nanoscale. His pioneering work laid the foundation for the field's terminology and also sparked widespread interest in exploring the potential of nanomaterials. His definition still stands today, and we can quote him as saying, nanotechnology mainly consists of the processing of separation, consolidation, and deformation of materials by one atom or molecule. So it still stands today. One of the most significant breakthroughs, though, came 10 or so years later in 1981, and this was with the invention of the scanning tunneling microscope, so STM, which you may have heard of. So scientists Binnig and Rohrer invented the STM. It was a pretty revolutionary instrument and allowed scientists to visualize and manipulate individual atoms with extreme precision, and this was not seen before. So for the first time in history, scientists could peer into the atomic realm with this amazing clarity and unlock all these mysteries of the nano world. This essentially paved the way for many groundbreaking discoveries that came in the decades following. So let's have a quick look into scanning tunneling microscopy and think about how it actually works. So you may have come across the scanning tunneling microscope if you're doing IB or A-level physics, perhaps. This is a brief video which explains scanning tunneling microscopy and quantum tunneling. Okay, so yeah, that was just a short video on the scanning tunneling microscope and quantum tunneling, which is a really interesting phenomena that you get at these very, very small sizes. Okay, so moving on and delving into nanotechnology in the modern era. So we'll be looking at some key advancements that have happened in the past couple of decades. We encounter quite a few groundbreaking discoveries in recent decades that have reshaped our understanding of nanotechnology. So we know that carbon is the fourth most abundant element in the universe, and depending on the arrangement of carbon atoms, takes on a wide variety of forms called allotropes. Carbon allotropes exist in unique properties. They have different strengths and electrical conductivities. So a question for you guys, carbon naturally can exist in two very different types. So what are the two allotropes of carbon that exist naturally?
Would they be diamond and graphite?
Yeah, fantastic. Thank you, Damien. So diamond and graphite are the most common and widely occurring allotropes. So we know they have very, very different chemical and physical properties. Since the 1980s, 3 additional forms were discovered between 1985 and 2004, and these have caused the current excitement among researchers about carbon nanomaterials. So the first one, fullerenes. Have any of you heard of the Buckminster fullerene? I think it may be part of the very small part of the spec in GCSE chemistry, possibly. Buckminster fullerenes are a very interesting type of carbon nanomaterial. So in 1985, it was a bit of a serendipitous discovery. So it was accidental. And some scientists at I think the University of Sussex discovered fullerenes. They discovered this kind of football-shaped carbon molecule. And this opened up many nanoscale possibilities. It's actually named after not the guy who discovered it, but instead the architect, Buckminster Fuller. And it's named after him because he popularized geodesic domes in the late 1940s. So fullerenes, like the Buckminster fullerene, can be naturally occurring. For example, it's sometimes found in soot. And the Buckminster fullerene, the most common one, has 60 carbons. And it forms this kind of alternating hexagon and pentagonal shapes, such that no two pentagons are touching each other. And the pentagons and hexagons wrap around to form this spherical shape. It's sometimes called a buckyball as well. Although it's really interesting and quite unique and has achieved or received quite a lot of research attention, there actually haven't been that many applications found for the real world for this, which is interesting. We then move on to the next groundbreaking discovery, which was the carbon nanotube. So in 1991, carbon nanotubes were discovered by Sumio Ijima, who published a groundbreaking paper in the journal Nature, which I'm sure you may have come across. And he reported the discovery of multi-walled carbon nanotubes. So in this picture, you can see a multi-walled carbon nanotubes where you have multiple tubes sort of stacked up within each other. You can also have single-walled nanotubes also. Cylindrical carbon nanotubes have a very high aspect ratio. So that's the length to diameter value. So the diameters are from about 1 nanometer up to maybe tens of nanometers. And the lengths can even be in terms of millimeters. So it's a very, very high aspect ratio. Fast forward to 2004, and this is when the scientists Scheme and Novoselov defied convention and they were able to isolate graphene. So as I'm sure you know, graphite is made up of layers of graphene, and until 2004, single layers of graphene were not isolated. So these scientists were able to isolate the single layers, and as you can see, they are composed of carbon atoms that are covalently bonded to 3 other carbon atoms arranged in this sort of hexagonal lattice. And they did this using nothing more than adhesive tape. So it was a pretty extraordinary feat and essentially catapulted graphene into the spotlight. And it's now got a bit of a wonder material status and seems like it has kind of limitless potential. So a question for you, what is so special about graphene and why is it seen as maybe a wonder material? Can any of you remember the properties of graphene that are a little bit interesting?
The layers can slide over each other because of the weak bonds that's between the layers, and then each carbon is only bonded to 3 other carbons, which means it conducts electricity.
Exactly, yeah. So very interesting electrical properties. It's one of the thinnest, but also one of the strongest materials, interestingly. So it's very, very strong laterally, as you can imagine, because of those strong covalent bonds. It's also a fantastic conductor of heat, actually better than all other materials, and is a really good conductor of electricity because of the delocalized electrons, as you correctly mentioned. It's optically transparent as well, but very dense, so it's impermeable to gases, including helium. Helium can't even pass through it. It's got a very unique combination of these properties and offers a very interesting material platform for the development of technologies as well. So potential applications in sort of wearable and super fast electronics, ultra-sensitive sensors as well, composite materials and coatings, applications in medicine, and so on. So we'll talk about some of those applications a bit later on. So since its first demonstration in 2004, graphene research has evolved into a pretty vast field with around 10,000 scientific papers now being published every year on a wide range of graphene-related topics. So since the 2010s, quite a lot of progress has been made in the synthesis and application of nanomaterials. Researchers have developed new fabrication techniques and explored new avenues for their use. And today, nanotechnology permeates almost every aspect of our lives and drives innovation in many, many scientific fields. So let's look at nanomaterials and think about the characterization and classification of nanomaterials. As we mentioned, we've looked at carbon nanotubes already, but we can also have many different types of nanomaterials as well, from graphene, as we talked about, to quantum dots, to polymeric nanomaterials, and so on. So first, let's think about the characterization techniques of nanomaterials. So we've already mentioned the scanning electron microscope. That was quite revolutionary in the development and characterization of nanomaterials and nanotechnologies. These are some other examples of characterization techniques that we have now to study, to synthesize, to characterize nanomaterials. So they're really, really important tools that are very useful to scientists in many fields that use nanotechnology. So we've got X-ray diffraction, atomic force microscopy. Some of these you may have come across before, for example, the transmission electron microscope. Some of them may be unfamiliar to you. Classification system. So these are the different classifications of nanomaterials, and they're essentially classed based on dimensionality. So the 0-dimension nanoparticles are essentially spherical ones. So things like the fullerene, things like single gold particles, the quantum dot as well. We have 1-dimensional nanomaterials. So these will be things like the carbon nanotubes that we talked about, polymeric nanofibers as well, metal nanorods as well, or ceramic rods. Moving then to the two-dimensional nanomaterials. So these are quite common as well. We talked about graphene sheets. We can have layered nanomaterials, or even plates. And then finally, we have the 3-dimensional nanomaterials. So these are our bulk nanomaterials, things like polycrystals or dendrimers as well. And each of these different types of nanomaterials have different applications as well. So what are nanomaterials actually made of? We know how to identify them and classify them, but what materials actually make up our nanoparticles? We've talked about carbon as being quite a common type of nanomaterial, one which is widely studied, but we can have many types of nanomaterials which are based on different materials. So we have silicon-based nanomaterials, for instance, metal-based as well. These are very common. We have polymer-based nanomaterials, and all of these we can classify into inorganic, organic, and then carbon as well, since carbon is the most common. And before we move on, we can just briefly mention the synthesis of nanomaterials and how do we actually engineer them and create them. So synthesis methods, essentially, we can break them down into two main types. So we've got the top-down approach or the bottom-up approach. So the top-down approach is where you start with a bulk material and essentially just break it down and deconstruct that bulk larger structure into nanoscale entities. So you break them down into the nanoscale. The other approach is starting out with atoms. So this is the bottom-up approach. And you can essentially, using scanning, tunneling microscopy, for example, assemble atoms and molecules into the structures that you want. And so you can precisely engineer your nanostructures using the bottom-up approach. So why does nanotechnology actually matter and why do we care about it? So the unusual physical, chemical, and biological properties can emerge in materials at the nanoscale. These properties may differ in quite important ways from the properties of bulk materials. The bulk properties of materials often change dramatically when we get to the nanoscale. So, for example, if we have metals with, let's say, a grain size of around 10 nanometers, this can be as much as 7 times harder and tougher than metals with larger grain sizes. So the causes of these drastic changes essentially stem from the weird world of quantum physics. So if we think about the bulk of any material, the properties are merely just the average of all of the properties across the atoms in our sample. As you make things smaller and smaller, you eventually reach a point where averaging and the law of averaging no longer works. So let's think about the properties of materials. In a bit more depth. So why is it that nanomaterials have these really interesting properties? Well, it essentially boils down to these two main reasons. And this is surface area, particularly surface area to volume ratio, and quantum size effects. We know about the surface area effects, and that the greater surface area to volume ratio means that nanoparticles make great catalysts, for example. And both of these effects lead to very interesting properties. So these are some of the interesting properties that we see in nanomaterials, from mechanical to electrical, catalytic as well, electromagnetic, even optical properties as well. So let's think about surface area first. Well, we know that as we reduce the size of a particle, we have a larger surface area to volume ratio. This makes the materials more chemically reactive. So some materials might be completely inert in their bulk form, but once we reduce them down to the nano size, they might be extremely reactive. This can also affect their strength or their electrical properties as well. And then thinking about the quantum size effects, well, secondly, quantum size effects can dominate the behavior of matter at the nanoscale. This affects the optical, the electrical, and magnetic behavior of materials and describes the physics of electron properties in solids when we have great reductions in particle size. So this effect doesn't really come into play when we're going from microscale to microscale, but it does become dominant when we're looking at the nanometer scale. Okay, so we'll move on to thinking about the applications of nanomaterials. Before we discuss this in a bit more detail, I'll offer a question for the group. So maybe try to think about an area or a couple of areas of science and technology that nanomaterials might be used in. What kinds of applications might we currently have for nanomaterials? So have any of you come across any applications of nanomaterials that you may have heard of before?
Could it be delivery of drugs and also microelectronics?
Fantastic. Yeah, so two really good examples there. Thank you. Drug delivery is a really important one, and microelectronics, yeah, we'll talk about both of those shortly. So we'll actually start with the medicine. So we have this kind of emerging field of nanomedicine, which is revolutionizing diagnostics, drug delivery, treatments as well. Nanomaterials can act as these kind of precision-guided missiles almost, and they can target diseased cells while sparing healthy tissue. And this minimizes side effects and maximizes therapeutic effects. So nanomedicine is defined as the area of medicine which uses nanotechnology, and there are a variety of applications of nanomedicine in treatments. So firstly, diagnostic applications. Well, we have nanoimaging agents where nanoparticles can enhance imaging techniques, things like MRI and CT scans, and this can make it easier to detect diseases early. For example, iron oxide nanoparticles improve MRI contrasts, and this helps doctors spot tumors more clearly. Might also be used as biosensors. So nanosensors can detect disease biomarkers quickly and accurately. One example is gold nanoparticles, which are used in rapid tests for diseases like COVID-19. These tests are kind of similar to pregnancy tests, for example. So it's a similar concept. Therapeutic applications as well. So drug delivery, Damien, as you mentioned. This allows for targeted drug delivery. So the drugs go directly to the diseased cells, and this reduces unwanted side effects on healthy cells. We've also got gene therapy as well, where nanoparticles can deliver genetic material like DNA or RNA directly to cells. So this opens up a huge number of possibilities for treating genetic disorders. We then have regenerative medicines, so tissue engineering, for example. For example, nanofiber scaffolds can help regenerate bone or skin tissue, and this can provide a framework for cells to grow. So some really incredible applications there. Antimicrobial applications we have as well. So some nanoparticles have interesting antimicrobial properties, which can help fight infections. Silver nanoparticles especially are a really good example. They have interesting antimicrobial properties and can be used in wound dressings and medical device coatings to prevent infections. So future scope of nanomedicine, well, where could it go? The possibilities are sort of endless, really. I think especially we'll have developments in smart drug delivery systems, so this will just keep getting better and better. So drug delivery systems that could maybe release drugs in response to specific signals from the body, like changes in pH or temperature. You might even have an increase in sort of personalized, tailored medicine. So we can have treatments tailored to an individual's genetic profile even. And then you may have heard of nanorobots. This is a kind of bit of a dystopian futuristic concept, but we're not that far away from it really. So we have the concept of nanorobots, which could perform medical tasks inside the body. These could be used to target and destroy cancer cells, for example. And this offers a whole new level of precision in medical treatment. So some really fantastic applications there. We've got applications in electronics. Damien, you also mentioned this. So nanoelectronics has been a recently developed field in electronics. And nanomaterials are kind of the unsung heroes of modern electronics because they have enabled the miniaturization of devices whilst also enhancing their performance and functionality. So applications from nanoscale transistors to flexible displays and quantum computing is really driving the next wave of technological innovation. So nanoelectronics involves using nanotech to create smaller, faster, and more efficient electronic devices. Firstly, we have the example of transistors and integrated circuits. Transistors are the building blocks of modern electronic devices, and nanotechnology allows us to make them incredibly small. For example, silicon nanowires and carbon nanotubes are being explored to create transistors that are just a few nanometers wide, and this can lead to faster and more powerful processors. Memory storage as well is hugely important. One example is the development of flash memory using nanocrystals. This increases storage density and reduces power consumption. Magnetic nanoparticles also, these are being researched to create high density storage solutions like MRAM. This is a lot faster and more durable than traditional memory. And then we have sensors. So nanosensors are highly sensitive and can detect tiny, tiny changes in the environment. And this is really useful for various applications. For example, we can think about gas sensors, which use metal oxide nanoparticles, and these can detect harmful gases at very low concentrations. So this could be really useful for environmental monitoring, for example, and safety. Consumer impact as well. Well, this has had a huge impact on consumer goods, as I'm sure you've all experienced. So things like smartphones and wearable devices. Nanotechnology is enabling the development of thinner, lighter, and more efficient consumer technologies. Things like LEDs are using quantum dots in displays, and these can produce more vibrant colors and consume less power than traditional LEDs. Flexible and stretchable electronics, we've also seen some work better than others, like the folding smartphones, for example. So nanomaterials like graphene and silver nanowires are being used to develop flexible and stretchable electronics. These might be integrated into wearable health monitors, for example, maybe even electronic textiles that can be worn like clothing as well. So what kind of future trends might we see? Well, I think the main one to highlight here is quantum computing, which is a hugely exciting area. This uses quantum bits that can represent both 0 and 1 simultaneously. Nanotech plays a crucial role here, with materials like our superconducting nanowires and quantum dots being used to create stable quantum bits. Quantum computers have a huge potential to solve very, very complex problems much faster than classical computers. And this would impact many fields like cryptography, drug discovery, material science, particle physics, and so on. We might also see an increase in energy efficient electronics also. So with the increasing demand of portable devices, energy efficiency is really important. Okay, and we'll move on to looking at applications in energy. So in the energy sector, nanotechnology is being used to enhance efficiency and sustainability. This includes the development of solar cells, wind turbines, also energy storage solutions, and so on. So this is going to play a huge role in how we combat the climate crisis and look at sustainable technologies for future energy generation. So solar cells to start with. Nanotechnology can increase the efficiency of solar cells, making them more affordable and viable. Wind turbines also, nanomaterials are used to improve the performance and durability of wind turbine blades. So things like carbon nanotubes and graphene composites make the blades stronger, lighter, and more resistant to environmental damage. So this increases their lifespan, decreases costs, and increases efficiency. Hydrogen production as well. So nanocatalysts can improve the efficiency of hydrogen production through processes like the splitting of water through electrolysis. For example, platinum nanoparticles are used as catalysts in electrolysis. And this is one way in which we can use hydrogen as a clean energy source. Energy storage solutions as well are being revolutionized with nanotechnology. So nanomaterials are really critical in developing next generation batteries with higher energy densities, faster charging times, and longer lifespans as well. So lithium ion batteries, for example, use silicon nanoparticles for the anodes, and these can store more energy and charge faster than traditional graphite anodes. Supercapacitors as well. These provide quick bursts of energy and have longer lifespans compared to traditional batteries. Graphene is used in this particular application. So since it has a very high surface area and conductivity, it's used to create supercapacitors that can store and discharge energy very rapidly. And this makes them ideal for applications that require quick energy delivery. So one example could be regenerative braking systems in electric cars. Energy efficiency also. So I've already mentioned the LED lighting and the use of quantum dots, but also potentially in insulation as well. So using nanomaterials in insulation for buildings, for example, reduces energy consumption for heating and cooling. Aerogels as well. These are made from silica nanoparticles, and they're highly porous and provide really good thermal insulation while being lightweight and transparent. So future trends. Well, I think some of the main future trends for nano energy will be improvements in grid storage. So improving grid storage solutions, which will be essential for managing the variable nature of renewable energy sources. Also, things like artificial photosynthesis. So researchers are exploring this area using nanomaterials to artificially undergo photosynthesis to convert sunlight, water, and CO2 into fuels. This could provide a sustainable way to produce fuel and reduce reliance on fossil fuels. There's many, many other examples of applications of nanomaterials that you can look into. Pretty much any scientific field will have some examples of nanomaterials and nanotechnologies. We've obviously got manufacturing and material science, cosmetic industry. So, for example, using zinc oxide nanoparticles or titanium dioxide nanoparticles, these are used in sun creams, as I'm sure you've heard of. This provides better protection against harmful UV rays from the sun. Nanotechnology is also used in food and agriculture, for example, to reduce reliance on pesticides and fertilizers. In the food industry as well, it's possible to enhance nutrients and flavor without using additives as well. It can also, nanosensors in particular, can be used for monitoring food quality and safety, detecting contamination and monitoring storage conditions as well. Of course, environmental cleanup is something to mention as well. So we mentioned nanosensors earlier. Nanosensors and nanoparticles can also be engineered to clean up industrial contamination. So, for example, making polluted water safe to drink or polluted air safer to breathe. So nanotechnology can contribute to improved filtration and purification processes. Okay, well, let's finish off by thinking about some of the future trends and how we can achieve them. So we've explored some of the current applications of nanotechnologies, and I've also discussed some of the future trends that we might see in areas like energy, medicine, and electronics. But how do we actually get there? So the horizon for nanotechnology stretches far and wide, and we have many exciting possibilities for exploration. We can see how nanotechnology can provide solutions for sustainability, and there is a huge scope for green nanotechnology as well. For example, for synthesizing sustainable nanomaterials, biodegradable nanomaterials as well. So we've got to implement these green chemistry principles as well as we're developing these nanoproducts. So how do we get there really? So nanotechnology requires a huge amount of interdisciplinary research. So many different scientists and engineers, biologists, they'll all need to work together to tackle complex problems and challenges and develop holistic solutions that can address multiple societal problems at once. We've also got to think about responsible innovation, and within this, think about the ethical and social considerations as well. We need to address the ethical, social, and regulatory concerns and ensure that we have the responsible development and deployment of nanomaterials. So this requires, thoughtful deliberation, transparency, and stakeholder engagement. So we have to ensure that we have robust frameworks for regulations with ethical guidelines as well, and engage the public and make the public more aware of the future of nanotechnology. And this can prevent or mitigate potential risks and maximize social benefits of nanotechnology. If we foster this culture of responsible innovation, we can hopefully navigate the complexities of this field and pave the way for a more sustainable and inclusive future. So that brings us to the end of the session on nanotechnology. Thank you very much for listening, everyone. If you have any questions, please feel free to ask. Otherwise, I'll be interested to hear your thoughts on the quiz. And if you have any questions on any of the quiz problems, then you can let me know. Otherwise, we'll end it there. Thank you very much for listening. If you'd like to access the talk afterwards, I think you can find it on YouTube or through Oxbridge applications. Thank you very much, guys.